Direct detection receiver. Called direct detection receiver, the architecture of the direct detection receiver shown slide. It consists of LNA. It is simple. It consists of antenna with LNA plus filter. This approach results in many practical limitations. Such of these limitations, like we need to tune these filters to capture after each times we receive signal. Software-defined radio (SDR). It is out of scope of this course, but software-defined radio system is a radio communication system which uses software for the modulation and demodulation of radio signals. So it uses software to perform communication system functions, and SDR performs significant amount of a signal processing in a general purpose computer or a reconfigurable piece of digital electronics such as DSP microchip or DSP chip. It is out of this reminder, but it's a cool area to study. You can just take it as self-study and get more information about LSDR in general. Quality factor. Quality factor, these terms we use to describe the quality factor for any things with related to the inductor or capacitor components in the circuit. So quality factor of a filter is a quantitative measure of how much loss the filter accepts or present. And now, lower quality factor indicates more losses. Practical filters, especially on chip filters, have losses and therefore low Q. It can be shown that the quality factor is inversely proportional to the fractional bandwidth of the filter. So when we increase the bandwidth or wideband bandwidth, the quality factor will be low, and when we have a narrow band or a smaller bandwidth, we have a quality factor, a high quality factor, or we can achieve a higher quality factor. In general, delta F is equal bandwidth over FC, where FC is the center frequency and the bandwidth is the 3 dB bandwidth we get it from the system. To have a small bandwidth at a high FC, a filter with very high Q is needed. As you recall from electronics, one can define the Q factor, or Q is equal F naught over F3 dB, where F naught is the center frequency and F3 dB is the 3 dB bandwidth. You get it from minus 3 dB. You get, as shown in this slide, the x-axis represent the frequency and the y-axis represent the response filter, and you can draw minus 3 dB and find the bandwidth of 3 dB signal. Channel selection. We have learned that most communication systems divide the frequency band into several narrower channels. The receiver should select each channel for detection. So we have two reasons: need for very sharp filter response to achieve divided the channel, and need for variable filters, which is tunable filters. Practical filters have low Q, so their fractional bandwidth cannot be reduced too much. It is practically very difficult to make tunable filters because you need to cover a large scales, and it will not be that easy to make it very accurate. The problem of channel selections, one can divide it into two questions. One, like we need to limit the bandwidth for better channel selection and limit the noise, or improving the NSRN case. Or the second, we need to filter signals at different frequencies, or making channels, or building up our channels. So the solution for the first problem is reduce the center frequency so that much lower bandwidth can be achieved with the same fractional bandwidth. It's a smart way to think about the problems, because when we get to reduce the center frequency, much lower bandwidth can be achieved with the same fractional bandwidth. The second problem, or the solution for the second problem, use a fixed filter and move the signal frequency instead, which means that we can call that what we called it the mixer process, when we having what we called intermediate frequency and create convert or transform the RF frequency using the local frequency to always get us a constant frequency, which we call the intermediate frequency. Mixer or multiplier conversion or frequency conversion. Frequency conversion devices or in electronics, it consists or equivalent to what we call mixer, and the mixer is equivalent to multiplier plus filtering. Frequency of a signal or frequency of a signal can be shifted or translated by multiplying it with another sinusoidal. So as you look at the slide, you have seen the model, what we call a mixer with a low pass filter. So the low pass filter here is just taking up conversion mixers. It determines the up conversion mixer or the lower conversion mixers, and taking what we call the intermediate frequency as an output. As you see here, we can shift the RF signals. Whatever the RF signals is coming here, you can manipulate it, the signal, and get what the desired intermediate frequency by changing the local oscillators or local frequency local oscillator. In this slide, we virtualize the frequency conversion in spectrum or in frequency domain. As you can see, we have the RF signals and multiplications with a cosine, one tone cosine at omega local oscillator, WLO. Okay, then it will be shifted by WN minus WLO, and then applying the low pass filters to select the desired frequency of intermediate. Heterodyne receiver improve the sensitivity. Instead of using the direct connections, we can using the what we call the heterodyne receiver. It is commonly used and standard. It is using it addition to solve the problems of channel selection. So we added the mixers to the LNA, then we added the filters. The filter here bandwidth of this filter determines the noise power KTB. طبعا by down converting the radio frequency signal RF to a lower intermediate frequency, much better selectivity can be achieved and SNR is improved as well. As you see in the slide, we have multi-channels and inserting our received at the antenna at the receiver received antenna. So we notice that the filter here is designed at intermediate frequency, and this filter will not be changing or tunable. We just need to change the WLO to get the intermediate frequency. So by changing the frequency of local oscillator, different WN will down convert to the same intermediate frequency, and this is the big idea of the mixer in general. Now, the choice of intermediate frequency and how can RF engineer designer select or choose the intermediate frequency. Now, by lowering the signal frequency to an intermediate frequency, you can reduce the bandwidth and therefore improve the SNR, and this is the big idea behind it. The lower we choose the intermediate frequency, the better performance we can get, but we can ask ourselves why we need to get the lower, or what the bound or the minimum value of intermediate frequency we have to get. In this slide, we described what we called image frequency. When we using a filter and down convert the RF to the intermediate frequency, or transform the frequency of the RF by changing the local oscillator to get us or achieve an intermediate frequency, we need to think about the image frequency. The image frequency, it means that when you receive it, you might receive a signal or a noise or another signals at what we called image frequency. At image frequency, as you see in in the slides or in the figures in the slide, okay, we have the desired and we have the image, which is, well, we will call it image frequency. When we multiplied it by cosine W local oscillator WLOT, image may come from another users or systems or etc., or maybe it will be a noise. When we shift these together and making a spectrum, they might be overlapping between the image and the desired signal, so it will be very hard to distinguish between them. So we need to fix this image frequency or clear it out before inserting to our mixer. So to clear out the image frequency components, one can propose a filter before the mixers, to what we call it image rejection filters. Note that the image rejecting filter is at high frequency, so that has limited selectivity. So we need this filters to clear out the components of image frequency. As you know, image rejection ratio, it means to study how we cleared out the component of image frequency. So we need to know at which level, because we cannot eliminate or completely 100% eliminate the component of image frequency using practical filters. So we need to define an image rejection ratio. This ratio is defined as the power of the received signals over the power of image signal at the intermediate frequency burst. Since IRR is a ratio, it is often expressed in dB. Now we have to think about the trade-off in choice of intermediate frequency. Sometimes we need to have the intermediate frequency as high as possible or as low as possible. It depends on the case, because I think in this scenario we have interference as a pulse. It is beside what we call desired channel. Then we have what we call the image at the image frequency components. We have the image rejecting filters, which is it will work and clear out the image components. Then when we apply the filterings and trying to get the desired signal, as you can see in insufficient filtering from adjacent signals or interference in the low intermediate frequency interference, it can be it can be eliminated, or it can be mitigated by filters in a good levels. So effective filtering of form adjacent signals as well. But the image rejections in low IF will be much bigger than when we used a high intermediate frequency. So in this case, you have to trade off between these two components, and in between you can find an intermediate frequency or appropriate suitable intermediate frequency for your application. In order to avoid the problem of image and channel selectivity, down conversion of a signal may be performed in two steps, especially if we have like a higher signals, RF signals is coming in giga, and we need to down converge of the signals into a low intermediate frequency. We can divide this step by two. As you look in the block diagrams, the image signals is removed in the first step. Then in the band interference is removed in the second step. This filter removes the image for the second filters as well. In this slide, we represent the two down conversion architectures. As you can see, we got the signals and remove the interference and eliminate the image components in a good way. Demodulation or direct conversion receivers. Now, the absence of an image greatly simplifies the design process. You can get it as an envelope, by the way. Channel selection is performed by on-chip low-pass filters. Mixing spurs are considerably reduced in number, suitable for IC or integrated circuits in general. Few external components are needed. Rx nonlinearity issues. As we talk about nonlinearity that dominates at the TX, it causes harmonic distortion, gain compression, intermodulation. Additional at the Rx side or at the receiver sides, they also causes harmonic distortion, gain compression, and intermodulation, plus desensitizations and cross modulation as well. As we spoke early about the harmonic distortions, it causes from the linearity. The nonlinearity, as we agreed in the first of this courses, we have the Taylor series model to modeling the nonlinearity for us. So let us take a single tone as an input, a single tone signal as an input x of t, and then applied it for the Taylor series model to model the nonlinearity of the system, and then the output will consist of several components. These components are the C fundamental frequency components, and we have a second harmonics and third harmonics. And so we need to filter these out to get the fundamental frequency pure. Again, compression our 1 dB points. We took it early at this class. Eventually, at large enough signal levels, output power does not follow the input power, and there is no relationship between them because the approximation about it will be a nonlinear, and the system will be unpredictable. So the power 1 dB point correlates well to loss of linear to lose of linear behavior, getting out of specification standards like LEV, AML, CPR, etc. So for the linear application, operation beyond this point is useless or unuseful. So we defined the 1 dB points to determine the linearity of the system. After this specification or after this point, the system will be useless, and we cannot predict the gain or any other parameters for the system or the behavior of the system overall. Modulation, also we spoke about it early in this class. We said that when we get two-tone test and insert two-tone to the amplifier in nonlinear behaviors, and we have the Taylor series models, we will get some new terms. These new terms, they are very close to the desired signal or to the fundamental, and as you can see in the slide, these are is very hard to deal with, and it's very hard to filter them out as well. Now, intermodulation, our IM3 products do not interfere with the main tune, so why we need to filter them out or to be worried about them? They interfere with adjacent channels. Usually, they interfere with the adjacent channels or the beside channels. Intermodulation products are troublesome both in transmitter and the receiver at the same level. As we explained it before, we have a two-tone test for intermodulations, and having these terms, the output of intermodulation test will give it as you see in the questions in the slides. Frequency separations are the same. Before compression, main tones grow with A, and intermodulation products grow with A square. From intermodulation concepts, one can define the intercept points, third intercept points as we call it, the input third intercept points, our output intercept points, our third output intercept points. These points will give us a range where the systems it can be predictable and eliminate the intermodulation if the system or the input level will be below this point. But after that the system will be useless and unpredictable as we see, and the intermodulation will occur. Desensitization, has it happened to you that you could not hear a weak sound when other near you speak loudly? When you imagine yourself in party and there is a loud response and you speak to your friends, but he cannot hear you because the interference around you, they are very strong. It is the same concept. So what we call desensitization and the receiver, it is the same as receiver blocking as known, is a form of electromagnetic interference where a radio receiver is unable to receive a weak radio signal that it might otherwise to be able to receive when there is no interference. Now, to explain the concept of it, at the input of the receiver, a strong interference may exit close to the desired signals, so it will block the receiving of the desired signals and most likely will get the interference because it is very strong compared to the desired signal. Desensitization related to gain compression. Think about the gain compression, like the small signal is superimposed on the large signal in the time domain. If the large signal compresses the amplifiers, it will also affect the small signal as well. So it will be like in gain reduction. So the their signal plus interfere will look like this. To think about the problem in mathematic way, assume we have an inputs like x of t equal a1 cosine w1 of t plus a2 cosine wt of t, where a2 akbar بكثير larger than a1, and A1 is the desired components and A2 is the interference at omega 2. When in compression, or when we have a compression or what we call the nonlinear behaviors, if we have alpha 1 and multiplied with alpha 3 less than 0, the receiver may not sufficiently amplify the small signal A1 due to the strong interfere of A2. And as I told you before, desensitizations, it's called receive blocker, or it's called blocker, creates problems when trying to keep the number of filters low. Intercept points of a cascade stages, we studied this before, and we found that intercept points at the last stages will be very important and very interest for us, because it will be multiplied by the gain for previous stages. So the denominated here for linearity in general will be in the last stages in opposite with noise figure. Mathematically speaking, one can find the overall OIB3, our output intercept point, our third output intercept points total for cascade system as is given in the equation on the slide. Please solve this example in this slide and pay attention for your observations. So when you think about, we have two stages. One stage in the first case we have two stages. One stage has J1 equal 10 dB and IIB3 equal 20 dBm, J2 equal 20 dBm, and IB32 equal 0 dBm. From my experience, the total IIB3 will equal minus 10 dB in this case. In the other cases, we just swap the places of the two stages, and we get the total IIB3 equal minus 3 dBm. and you can observe that the nonlinearity for the last stages is dominated always. Thermal noise is dominated for the RF in general, especially for large, when we use dealing with a large frequency due to random movements of electrons and resistance at temperature T Kelvin generate a noise. The average power of this noise across a match load measured over P hertz at any frequency is given by KTB, where the K is Boltzmann constant and the T in Kelvin and the B is the bandwidth. In this slide, we introduce the sensitivity of the receiver, or how we can calculate the sensitivity of the receiver, or the minimum power of the received signals to receiver be able to detect it. So the sensitivity is defined as the minimum signal level that a receiver can detect with acceptable quality. I drive this by in the slide and during the equations. So we found that the power sensitivity is equal minus 174 dBm per hertz. This numbers came from, if you get back to the KTB, it is a Boltzmann constant with the room temperature in the Kelvin, 293 in the Kelvins. If you find the dBm from them, you will find it like minus 174. So be attention that if I change the temperature for this system, this number will be changed. So the power sensitivity, as we say, it is like minus 174 dBm per hertz plus noise factor plus 10 local bandwidth plus signal to noise ratio minimum. The first three terms, as you see in the slides, we call them the noise floor. So when I ask you about the noise floor, it will be calculated minus 174 dBm plus LNF plus 10 local bandwidth. Dynamic range of signals which could be processed by the receiver is limited always. So lower end, and we define the lower end and the higher end. A lower end is signals should be strong enough to provide the desired SNR, and be attention that the lower end is close to the sensitivity as well, our power sensitivity for the receiver. A higher end signals should not push the receiver into nonlinear equations, which is the third intercept points, or power 1 dB. So we define the dynamic range, which is the maximum tolerable desired signal power over the minimum tolerable desired signal power expressed in dB. As you can see in figures, we have our sensitivity, and this is what we call the lower end. A receiver integrate noise as well, and we have what we call the dynamic range. It is from the maximum higher end minus a lower end, you can find dynamic range. Also, we have what we call the spurious free dynamic range, SFDR, for our receiver. It is more accurate than a dynamic range. It depends on the power minimum, which is equal noise level plus the SNR minimum, and the power maximum is equal second intercept points, 2 multiplied with the third intercept points, plus a noisy level over 3. You can define its equation in the next slide. In this slide, we express the SFDR, how we can calculate the SFDR as an equation 2.157 and 150s. In general, SFDR represents the maximum relative level of interference that a receiver can tolerate while producing an acceptable signal quality from a small input level. In the last, as a self-study topics, you can study about the automatic gain control. At some point along the receiver chain, circuits should operate with fixed signal levels, so we can change our gain depending on the power of the signals to keep same or fixed signal levels during the cascade system.